Great. So we're going to find a very famous identity known as a compound angle identity. And a compound angle is simply a sum or difference, or an adding of multiple things. If you've taken actually grade 9 tech, you would know that a compound cut is when you have a cut with an angle and another angle is superimposed on top of it. So suppose we wanted to know the sine of x plus y. We've got the sum of two angles. And a great reason for wanting to find this is, and I'll go a couple pages over here to show you. Suppose you wanted to know the sine of 5 pi by 12. Well, we don't actually know the sine of 5 pi by 12, but we do know that 5 pi by 12 is 3 pi by 12 plus 2 pi by 12. So instead of finding the sine of 5 pi by 12, I'm going to find the sine of 3 pi by 12 and 2 pi by 12. Again, that might seem awkward until you go ahead and simplify to pi by 4 plus pi by 6. And now these are angles that we may know sines, cosines, tangents, whatever of. So we're hoping to come up with a rule that allows us to find the sine of this sum so that we can find the exact value of the sine of this angle. Well, with that example kind of in mind, it's actually kind of useful because sine of 6 pi by 12 would be pi by 2, which would be right there. Sorry if you're hearing that sound in the background. It's either my dishwasher or Miss Gregoris YouTubing. I think that's the Masked Singer. I'm not sure. So 6 pi by 12 would be right there. 5 pi by 12 is probably somewhere up here. And let's go ahead and draw it. So this is our angle that we're looking for. And we know that it's the sum of two angles. It's the sum of this angle from here, which we'll call x, plus this angle there, which we'll call y. Now, for x, we've got this triangle. And it's a right triangle. And in our particular example, it was pi by 4, but we're going to do this in general so that we come up with a formula or an identity. Now, the next few steps are really going to help us to find one thing, because the sine of this compound angle, this whole angle right here, would be the length of this line divided by the length of the hypotenuse. So the length of the opposite of the angle divided by the length of the hypotenuse. To find that, we have to do a little bit of trickery. So that trickery is going to involve a couple of colors. And I'm going to draw my triangle in a few different ways here. So I've got I'm going to keep this as my dark black triangle. And I'm going to create another triangle by extending a line up to here. Now, this green line that I've added is perpendicular to the original angle for x, and so I now have a right triangle that goes from the origin up to the end of the hypotenuse from my angle x, and then up to the end of the hypotenuse from my angle x plus y, that entire red thing. Now, I'm going to add one more triangle. I'm sorry, this red line I should have done this slightly differently. If we could just really imagine nicely that that red line intersects right there, nice and neat, so that this point line, this line, and this line, the black line, the red line, and the green line, all line up congruently at that single point. They intersect. They've got a common solution. So I'm going to add one more piece to the puzzle here. I'm going to leave it in green, I suppose. I'm going to run from the intersection across to the altitude another triangle. and it's going to form a right angle. So this green line and this red line are perpendicular to one another, and all four of these lines meet at one single point. Now this is going to get pretty confusing unless we have some sort of way of labeling. So let's go ahead and label, and I think we'll use purple for labeling. Like my origin is A, because that's where I like to start. I'm going to go to the very top and call this B. I'll keep going around clockwise and call this point C, which means I'll call this point down here D, which means I'll call this point right here E. And then I'll just kind of keep going up and through. So I'm going to call this F, and I'm going to call this point G. So what I'm eventually going to do is I'm going to try to come up with a way that using just angles X and Y, I can determine the length from B to G and G to F and F to E. Because if I knew that length and I knew this length, I would know the sine. It would be this one divided by this one. So this particular diagram, you should hit pause and definitely copy it out because we're going to be referring to it. In fact, I'll have it right beside me to help guide. So before I tear the page and move off, let's mark a few more things on this diagram. You can see angle CAD is given as X. Well, angle CAD and angle FCG are equivalent. And they're equivalent because GC is parallel to AD, which means that AC is a transversal. And by the transverse parallel theorem, I can say that this angle is X. Now, I can kind of go a little bit further here too. Because I know that angle FCB is a right angle, because I constructed it to be so, that means that this angle in here is whatever pi by 2 minus x is. So I'm just going to call this something else right now. We'll call it z. And I know that z is equal to pi by 2 minus x. Because pi by 2 plus x, x plus z should be equal to pi by 2. So that's what z is equal to. Now, if z plus g, which is just pi by 2, plus whatever angle is up here, they all add to pi. So I can say that angle GBC plus pi by 2 plus z is equal to pi. And that's because triangle CGB needs to have pi radians. Now that I know that it needs to have pi radians, I can go and do a quick little addition here to figure out what angle GBC is. Of course, this is pi by 2, and z is pi by 2 minus x. So that means that pi by 2 plus pi by 2 is simply pi. So I can subtract pi from both sides. That will cancel, which would leave me with angle GBC is equal to x. So I know that that angle up there measures x as well. And now I have all the information I need for my diagram. So